Hi everyone. Today I want to tell you about joint work with Oded Goldreich from the Weizmann Institute on robustly self-ordered graphs, constructions, and applications to property testing. Plan is simple. I'll tell you what the basic notions are: asymmetric graphs, which are self-ordered graphs, and then this robust notion of asymmetric graphs, which we called RSO, robustly self-ordered. Then we'll talk about reductions from ordered to unordered structures using these RSO graphs and see applications to property testing. And at the end, I want to demonstrate one explicit construction of such RSO graphs. So order obviously is very important. And we want to talk about ordered and unordered structures. Typical ordered structure is a sequence or words or sentences in a language. So for example, here are two words, and they are obviously different despite the fact that they have the same letters, because we read them from left to right, so there's an implicit numbering of the coordinates of each word. That's an ordered structure. In unordered structures, and the main example is graphs, we have for example, these two objects that look different, and actually we don't want to count them as different because if we number the vertices 1 through 5 as in the left, we can have another numbering of the vertices on the right, and we see that the two graphs are the same with this ordering. So here the right notion is isomorphism for unordered structures. So using this, let's define symmetric and asymmetric graphs. On the left, we have the pentagon numbered and the set of edges E of this graph with this labeling. And now we can look at permutations that permute the names of the vertices, which will always be numbers 1 through n. We call such a permutation an automorphism if it preserves the edge set E. If it's a trivial permutation, doesn't move any vertex, then it's obviously an automorphism because we have the same set of edges. But in this, so here's this example. But for the pentagon, there are also non-trivial automorphisms. For example, we can shift the numbers cyclically, or we can take a reflection, and we get non-trivial automorphisms or symmetries which preserve the edges. For example, that's a shift, and that's a reflection. They preserve the graph. So a graph is asymmetric if it has no non-trivial automorphisms. In other words, if the permutation pi is not the identity, it moves something, then it moves some edge. In other words, the symmetric difference between the original edge set and the permuted edge set is non-trivial, it's positive. Asymmetric graphs, let me give you some examples. The smallest asymmetric graphs have 6 vertices in them, and here you have all of them. So no graph here has a non-trivial automorphism. If you want regular graphs, you have to go higher. That's 12 vertices is the smallest you can have for a regular graph that is asymmetric. It's not hard to see that it's a counting argument that almost all the regular graphs are asymmetric. And it's much more interesting to think about explicit constructions. You can try. We'll see even stronger explicit constructions later. Okay, so these are symmetric graphs. You can define them in several ways that are useful. That's the original definition I gave you. Equivalently, a graph is asymmetric if no matter what other isomorphic graph G I give you, the isomorphism between them is uniquely determined. So it's isomorphic. There is an isomorphism, but it's unique. Again, equivalently, a graph is asymmetric if its vertices can be uniquely named from 1 to n. You can assign canonically a naming to the vertices. One way to do it is, because of this property, non-trivial automorphisms, for example, all adjacency matrices in over all namings will be different, so you can take the lexicographically first. But there are many ways to do it, so pick any canonical naming from now on for an asymmetric graph. Here's the same asymmetric graph, and I picked one canonical ordering here just to say that there is one. And because of this property, we call an asymmetric graph also self-ordered, sort of orders itself. Of course, the fact that it can be, we can find, or there exists a unique naming, raises an efficiency question, which we will deal with later. Okay, why are they good self-ordered graphs? Because they afford reductions from ordered to unordered structures in an obvious way, in fact. So here are the two examples. It's two sequences that are different because they live in an ordered world, but we can just place them on the vertices of the graph above according to this unique naming of the vertices. And then, they are not isomorphic with these names, with this alphabet labelings. So because of that, and in fact, it doesn't matter how I give you the graphs, I can rotate them or draw them differently. Because of unique naming, you could put it in the right order and compare the letters. So this is used for reductions between ordered and unordered structures. It's not a new idea. It was used in logic and descriptive complexity for studying logics with order relation and without order relation. And I just want to point out that if you don't like labeled graphs with alphabet letters, it's clear that you can instead put some small gadget graphs that correspond to the characters in your alphabet. Around every vertex, put the appropriate little graph. For example, if the alphabet was binary, we could put a self loop on a vertex if this bit is 1 and otherwise not put a self loop. Okay, so we'll use it later. Now, these graphs are, were applicable in logic sequential algorithm setting where we have a complete access to the graph G and we can find this unique naming of the vertices. But we want to look at the setting where you have only sampling access to the graph, like in property testing or statistical applications. And then it's not good enough. What you need is a robust version of this notion. And that's what we call robustly self-ordered graphs that I now define. So again, reminding you that a graph is self-ordered if whenever you move a vertex, you move an edge. I wrote it in this particular way. So unfixed vertices, I wrote as a symmetric difference of the vertex names before and after the permutation. If this is positive, then we move a positive number of edges. In a robust version, what we want is for any fraction alpha, if we move an alpha fraction of the vertices, then we must move an alpha fraction of the edges up to a constant factor. This has to hold for any permutation, and any alpha. Alpha can be a constant, can be 1 over root n, anything. The same proportion has to move as in the vertices, also in the edges. So just to get a sense for the two regimes we care about in the talk, sparse graphs, if you move k vertices, you must move omega of k edges. That's just because the number of edges is linear. And in the dense case, if the degree is linear, moving k vertices means that you must move k times n edges. And that's for every k. So that's, in a sense, in a clear sense, RSO graphs are as far from being symmetric as possible. Okay, so now I want to talk about constructing them. So here's the definition. just to show that they exist in abundance, in fact, almost every d-regular graph, no matter what d is RSO. This is not hard to do, like with the asymmetric graph. And we want to show explicit constructions in both sparse and dense regimes. In the sparse case, we have two different constructions. The first one is direct. In fact, I'll show it to you. It goes by a reduction to expansion of an auxiliary graph. It seems that it's natural to expect that RSO graphs are somehow related to expansion, but they are not in a direct way. We have a different construction, which is iterative. So the nature of it is different, but also the result is different. In this iterative construction, we can generate RSO graphs that are extremely disconnected, very far from expanding. In fact, they have tiny connected components of logarithmic size. So it's not directly related to expansion. In the dense case, we also have a direct construction. It goes by reduction to a different pseudo-random object, non-malleable to source extractors. For those who don't know it, let me just note that these are among the most complex to construct pseudo-random objects that I know of. Let me explain what I mean by explicit construction. This is in the strongest possible sense, strongly explicit, namely adjacencies can be computed in polylogarithmic time. In other words, the graph can be exponential, and in the sparse case, I give you a vertex, you look at it in polynomial time in its length, you can tell its neighbors, and in the dense case, given two vertices in polynomial time in their length, you can tell whether they are connected or not. So that's the strongest notion of explicit construction, and we need it. I want to talk about this efficiency of finding the ordering. So let's fix an RSO graph, fix a vertex names. And what do we want? Suppose somebody handed us an isomorphic copy, G prime of G. So let's say it's sigma of G. We know that this isomorphism is unique, and what we want is to find it so that we can know what the real name of every vertex is. In the full access to G prime and G, then it's a graph isomorphism problem. It can be solved in polynomial time for constant degree and in quasi-polynomial time in general. But we don't care about this regime. We care about having local access to G prime, oracle access. And here we develop new local self-ordering algorithms for this type of graphs. So more specifically, the theorem is that you have explicit constructions of d-regular graphs, which are RSOs, and given an oracle access to any G prime isomorphic to G and a vertex I, we can compute both the image and the pre-image of I under this unique isomorphism sigma. So this is computable in polylog time as well. What do I mean by oracle access? What I said before, incidence oracle in the sparse case, and that we do in this paper. We also have results in the dense case, but we do much better in a subsequent paper that I will mention later. But I will deal here mainly with the sparse case. Okay. What I want to show you now, and it will be very natural, is the application to property testing. So I'll remind you the setup. I'm sure most are familiar with this. We have some large universe U, which has some metric or distance on it. And we have a subset in it, P, which denotes just, we call a property. It's an arbitrary subset. And we want to distinguish element of P from elements which are far from P. So we call F epsilon the objects that are at least epsilon away from any objects in P. And of course, we want to do it fast. That's the whole point of this distance. So a Q epsilon tester is a probabilistic algorithm that on input X in the universe just makes Q queries to X. So looks only at Q coordinates of this input X and using them only must decide in the case that X is in P, must accept with high probability. If it's in F epsilon, it must reject with high probability. And if X happens to fall in this gray region between, close to P, then it doesn't matter what answer the tester gives. It's allowed to accept or reject. So that's a tester. And imagine that the length of the inputs is n, then the following theorem, it's two results, two applications to property testing of sparse graphs. I'm not defining the model and the distance exactly, but it's intuitive. We have a universe which is a universe of unordered elements, namely of graphs, irregular graphs, with constant degree. One result is an efficiently computable property P, graph property, such that every tester with the constant epsilon must ask a linear number of queries to be a tester. Another result is an exponential gap in the query complexity between testing, which I defined, and tolerant testing, which I didn't define, and I will not, but anyway, another new result. But the point is, we don't have to get into the result. The main point is that the way this theorem is obtained, as you expect, this is obtained by direct reduction from similar results in the ordered regime, in the case that the properties over ordered structures, like sequences, which were known. So just applying reduction using this RSO graphs, we get this result. So let me spell the reduction, which is general and maybe has other more applications. We start with any property of ordered sequences. We fix a RSO graph with the same size of vertex set as the length of elements in U. And then we encode this sequence in U, like I showed you earlier, into a graph. For example, adding a self loop at vertex I if and only if the ith element of X is 1. Now we can define, a new property P prime, which is a subset of U prime, the universe, which is all irregular and vertex graphs. The property P prime is the obvious one. We simply take all X which have the property in P. We construct G sub X, and then we take all the permutations of this graph G sub X, because we want the result to be a graph property, not just a property. And what do we know about this reduction? Well, it's obviously local in the sense that to know xi from the graph, we just need to query vertex I and its neighborhood. It's distance preserving. That's very important for any result about property testing, because distance is key. It's not hard to see using the RSO definition that the distance between any string X and the property P originally is preserved when you move to G sub X or any permutation of it to P prime. And finally, the local ability to locally compute the polylog time, the unique isomorphism, translates, well, if you we compute the image of I, this yields from upper bounds in the ordered case, upper bounds in the unordered case, and the pre-image, you get the same for lower bounds. So that's how it's used. It's very natural and simple. So the last thing I want to show you is some construction of sparse RSO graphs. This construction will be not just of undirected graphs, they'll be directed. Edges will be colored with a few colors, and they may be multi-graphs. All these green things can be eliminated, but I will stick to this case because it's simpler to describe. So what do I mean by a directed color graph? Well, it's just a graph that is defined by D permutations. You can think of each permutation, sigma k, as associated with a color class, k. So really the edge set is the union of D 8 sets, one of each color, where E sub k is just the pairs V sigma k of V moved by the case adjacency permutation. Okay, so that's a directed colored graph. And now I want to define an auxiliary object that's important for the analysis. It's a pairs graph, so it's graph on the pairs of vertices in G. And the edges of this graph are just, you take any pair U sub V, and for every permutation sigma k, you look at where this pair moves to. So the same action on singletons in G is moved to the action on pairs in G star. So it's simply the graph of these permutations acting on the pairs. And the main theorem is that if G star is expanding, then G, the original graph, is RSO. Okay, so let me give you a sketch of this proof of this theorem. So it's the definition, and that's the theorem. So what should the proof do? We are getting an arbitrary permuted copy, G prime of G. So pi of G is G prime. And let T be the set of vertices that are moved by this permutation. Okay, so what do we want to show? We look at the symmetric difference between the old and new edges. They are naturally partitioned by color. And we want that this sum of these symmetric differences to be roughly up to a constant, the size of T, the number of moved vertices. So how do we do this? We look at another set, a set in G star. This is a set that is simply the pairs V pi of V. They are not edges of the original graph. It's just a set of pairs, right? Obviously, for every V that is in T. So it's the same size of as T, and then now let's see what happens to it. If we move it by sigma k, let's assume for a second that we get something out of T. Let's say that this sigma k moves this pair out of T star. Then I claim that we get an error, we get something in the symmetric difference of the case color. So I'll show you this in a moment, but let's see why it finishes the job. Well, remember that G star is expanding. So out of any set, like T star, the number of things moved out is linear in the size. So it's omega of T. And since that's exactly what the definition of RSO was, we know that G itself is RSO. Now, why does it happen? Why is this implication in the bottom happens? It's simply this being moved out of T star really means that sigma k and pi don't commute on V. Let me do it by a picture, it will be clearer. Here are the objects we care about. We look at V, and horizontally we see the action of pi, vertically we see the action of sigma k. And we are interested to know what happens to this edge, whether it will be moved by pi to same colored edge or not. And so we want to know what's happening here. And well, if sigma k was moving pi of V to that point, to pi of sigma k of V, if they commuted, then this pair will also be in T star, but we know it's not in T star, so we must have an inequality here, which means that actually sigma k goes elsewhere, and therefore this edge is not moved to a similar colored edge. It's either moved to another color or maybe to a non-edge, but that's the source of the error. Okay, so finally, where do we get such graphs so that the pairs graph is expanding? Here we need some bits of using expanding Cayley graphs. This is a special case of a general construction. Let me tell you about this special case. So take the group H, which is SL2Q. This is a group of 2 by 2 matrices over the field of Q elements, determinant 1. Here's a set of generators for it, and this will be the permutations that will help us define our graphs. So So these are just 4 elements of SL2Q. So the degree of our graph will be 4. Selberg proved a very important, powerful theorem that implies that the Cayley graph of H with its generating set, the Cayley graph is just the vertices are the group elements, and you just look at how they are moved by generators. These are expanders. And these are not the graphs we are going to use because clearly Cayley graphs have lots of symmetries. What we are going to use is a corollary that if a Cayley graph is expanding, all actions of that group with its generators or on any set gives also an expanding graph as long as it's connected. These derived graphs are called Schreier graphs. So the one we will take is the Schreier graph of the action of H on what's called P1, the projective line, which will be our set of vertices. This is just simply the set of numbers from 0 to q minus 1, namely fq, and the point at infinity. And the action of a group element on this set is the famous Möbius action. So matrix ABCD acts on X simply by taking it to AX plus B over CX plus D. If you define division by 0 and multiplication by infinity appropriately, you see that this is a group action, so it composes with the group multiplication. And it's transitive, so it's a connected graph, therefore an expander in this case. And also the action on pairs, the same action when defined on pairs, is also transitive. So it's also an expander. So it satisfies the condition we wanted. G star is expanding, and so G must be an RSO graph. So it's one simple and easy to define explicit construction of RSO. Let me conclude. The main points, we gave a new definition of a pseudo-random object, RSO graphs. We showed explicit constructions, both in the sparse and dense case, and turns out in the intermediate cases as well. These constructions also admit local self-ordering, which is critical to the application in property testing. And we have a general reduction from ordered to unordered structures that we can use to import results from the ordered setting to the unordered setting. So some follow-up works. I mentioned that in a follow-up work, we managed to build local self-ordering procedures for the dense case, and we have more applications of this property testing. In another construction that I didn't tell you about, brought up this connection, and we wrote a different paper. So it's RSO is connected to another pseudo-random object, to error-correcting codes, in this case to permutation codes. They were studied, but results were pretty poor. We get constant rate permutation codes with efficient encoding and decoding procedures. So basically solve the general problem for these codes. In another paper, ordered studies relations between these two notions that you can define independently, and yeah, the connections are very interesting. Open problems, there are many, I think, these constructions, and especially the self-ordering procedures, can be used even in the classical setting, can have more applications. And as I showed you, RSO graphs are connected to expanders, extractors, error-correcting codes, and it's really would be nice to have a better understanding of these connections. Thank you very much.